Okay, so today I'll conclude the talks about dimer algebras and core algebras. And there was one question that was a good question from Wednesday. I just wanted to answer really quick, which was I had removed these two cycles. And the question was, well, the quiver I was removing the two cycles from it had a lot of two cycles in it. And it's not removing all two cycles like you do with the quiver mutation. It's just the unit two cycle. So it's a unit cycle that's the two cycle that you remove. So not all two cycles, just the unit two cycles in this case. Oops. Okay. So this is the primary question in kind of this part of geometric representation theory is how is the representation theory of a non-commutative algebra related to the geometry of its center? And so you can ask questions like, does the smooth locus of Z, the center, parameterize the simple A module isoclasses, maximal K dimension? You could ask if the commutative resolutions of Z parameterize families of indecomposable A module isoclasses. So that's exactly what we looked at on Tuesday. There's other questions like, are the global dimensions of localizations of A at subvarieties of the algebraic variety of the center equal to the codimension of the center? And then you can ask questions that I'll get to later today, like with boundary algebras and cluster structure. So these all kind of have this interaction between geometry and representation theory. And without the framework for geometry for non-Noetherian commutative rings, we would have no hope of asking these questions if Z is non-Noetherian, which is almost always the case for dimer and core algebras. So I just want to kind of briefly review the main ideas I had on that we talked about on Wednesday. And the first one was cyclic contraction. So a cyclic contraction is, so these would just kind of be the ideas of what I had defined. A cyclic contraction psi from a non-Noetherian dimer or Gore algebra to a Noetherian dimer or Gore algebra is obtained by contracting a set of arrows of Q such that the cycles of Q are preserved. So you contract some number of arrows such that the cycles in the quiver are preserved. And so Q and Q prime share the same cycle structure called the cycle algebra. The other notion that we talked about was that of a depiction. So a depiction S of a non-Noetherian commutative integral domain R is a finitely generated algebra S such that S sits between R and the fraction field of R. So S is as close to R as possible in a suitable geometric sense. So that is, we can understand the geometry of R using S. So specifically, max R, and by max R, I mean the maximal ideals of R with the Zariski topology, looks exactly like the algebraic variety max S, except that there are some positive dimensional subvarieties that are identified as single points. These are kind of smeared out points since they have no points in their interior. And the magic is that for a dimer or Gore algebra, this finitely generated algebra S can be obtained from its representation theory. This is the cycle algebra. And the depiction of its center is an intrinsic property of the dimer or Gore algebra itself. And just as an aside, I began kind of making up these various notions for cyclic contractions, the cycle algebra, depictions, positive dimensional close points, and Gore algebras about 10 years ago to study what were generally kind of regarded as the bad or inconsistent dimer algebras. Okay, so I want to give a kind of a real concrete example with the how the Gore algebras work. And so recall the non-cancellable dimer quiver on a torus that we looked at on Wednesday. And here, this arrow right here is, we'll see, is not contained in any simple matching, so it's non-cancellative. But we will actually see that in a minute. Okay, so now this blue path here and this purple path, so this is drawn on the cover, the covering quiver of, this is on the torus and this is on the cover. They are not equal in the dimer algebra. So you can see, you can try to move this blue path to this purple path using the dimer relations, but here you have 2 arrows, so that's no good. And here you have 2 arrows there, so you can't move this either. So it's the blue path is stuck and the purple path is stuck, so you can't move them. However, they're equal in the Gore algebra lambda, since they are a non-cancellative pair. And you can see this by using this orange arrow. And on a torus, lambda is equal, so the Gore algebra, lambda is equal to the dimer algebra A modulo the differences of paths of non-cancellative pairs of paths. And just to kind of caution, this equality here does not hold on higher genus surfaces. So it actually does not hold. These are not equal on higher genus surfaces. Okay, so let's to kind of do this explicitly. Here's an example of a simple matching. So all the arrows in orange belong to the simple matching. And you can see it's a simple matching because if you follow the black arrows, you can get from any vertex to any other vertex on the torus. Of course, not in this covering quiver, but on the torus, you can see you can start from any vertex and get to any other vertex on the torus. And so this is a simple matching. So each unit cycle contains precisely one of these orange arrows. And so what you do then is wherever you see an orange arrow, you put a variable, let's say X. So now we have an X sitting on each of the arrows that was in that perfect matching. Okay, we can also do this with a non-simple matching. The red arrows here are in a non-simple perfect matching. So you can see, okay, if you start at this vertex here, there's no way you can get to that vertex following black arrows, because it's with the red arrows being, if you omit these arrows, then this is like a source. And so you can't get to that vertex. So this is not a simple matching. It's a perfect matching that's not simple. And each unit cycle contains precisely one of these arrows. So just like we did up here, wherever we see a red arrow, we put a variable, let's call it U. So now we have a U wherever there was a red arrow. Okay, so this is how it works explicitly, and you go through and you look for all of the perfect matchings in the quiver. Okay, so when you do that, this is what you get. So here the X, Y, and Z, the orange variables, all are simple matchings, and the red U and V variables are non-simple perfect matchings. And so here you see we have a monomial sitting on each arrow. And now if we go back to this example with the blue and the purple path, well, if you follow the blue path, now you have Y times Z times Z times XU. That's equal to X times Z times DC times YU. So they have equal eta bar images, which is X, Y, Z squared U. So their eta bar images are equal. And so in the Gore algebra, just like we had before, the blue and purple paths are equal. They're not equal in the dimer algebra, but they're equal in the core algebra. And just in case anyone is wondering, the word core, since surface algebra was already taken, core is Klingon for surface. Okay, so there was one, the last theorem that I had put on Wednesday, I had left out an assumption, and I thought about it after, and I really should have the assumption, so I just wanted to restate this quickly, and then I'll go on to the higher genus surfaces. So recall that the nil z was the nil radical of the center z of a dimer algebra, and z with the hat is its reduced ring. So z mod its nil radical. Then the theorem was that if psi is a cyclic contraction of dimer algebras from A to A prime on a torus, and here so A is non-Noetherian, A prime is Noetherian, the nilpotent central elements of A are precisely the central elements in the kernel of psi. So we saw that the reduced center is an integral domain. And this was the thing I had said z hat and r are equal, but you really need them to be normal. And so z hat is a subalgebra of the Gore center R, the Gore algebra center R, and their normalizations are equal. So they have equal normalizations. And so if R is normal, then these, and yeah, if these rings are normal, then this is fine. We have equality between the reduced ring and R. Furthermore, though, R is normal if and only if it's of this form K, so that's our ground field K, plus some ideal J in our cycle algebra. So this was exactly of the form that we looked at the beginning on Wednesday with depiction. So this is what the algebras in that section look like. So consequently, if the reduced center is normal, then it's K plus some ideal in the cycle algebra. And the main thing, though, is just that regardless of the relation of the reduced center to R, it is depicted by the cycle algebra S, and therefore the Kroll dimension of the center, which is equal to the Kroll dimension of the reduced center, is equal to the Kroll dimension of R, which is the Kroll dimension of the cycle algebra, because it's a depiction, and that's equal to 3. And I just wanted to quickly give an example where you see the center is non-normal, and this is a non-Noetherian dimer algebra with a non-normal center. So they all kind of have that, all the examples I know have this form where they kind of look like they have these nested unit cycles. Perhaps this is always true, I don't know, but that's an open question. But this will have a non-normal center. And one where the reduced center is not equal to R is here. And you can see this monomial x, y, z squared is in R, but it's not in the reduced center. And you could see here, if you go, say, from this vertex, you have z1, you go up here, you have x, z, y. So there's that monomial, so it's hitting all these vertices. You can also go along this, and then it comes out here to the unit cycle here. So it gets that vertex and that vertex. You can do it up at the top here, z, and you go along here, and you get this monomial x, y, z squared. And so it gets that vertex. But we still need to get that vertex, but we can get that vertex because it goes z times 1, and then z times y times 1 times x. And so we get that vertex there also. So we know that this x, y, z squared is in R. And then you can, it's more work to see then is that it's not in a central element in the dimer algebra. So these are just some examples to see how diverse things can happen with with these algebras. Okay, so now we ask, what is the central geometry of a non-Euclidean dimer and Gore algebra on higher genus surfaces? So let Q be a dimer quiver on a surface sigma with fundamental 2n-gon P. So specifically, sigma is a surface obtained by P by identifying the opposite sides of P and all the vertices around P. If P is a 4G-gon, then sigma is a smooth genus G surface. So something like this. If P is a 2 times 2G plus 1-gon, then sigma is a genus G surface with a pinched point. So now set sigma to be the product of all the variables, so all the perfect matchings. And this will be the eta bar image of any unit cycle, just by the definition of perfect matching. A perfect matching is a set of arrows such that each arrow is contained in precisely one unit cycle. So from that, it follows that the eta bar image of any unit cycle will be the product of all the variables. The first thing to note is that if sigma I and sigma I prime are 2 unit cycles at a vertex I, then in A and the dimer algebra A and the Gore algebra lambda, these two will be equal. In the Gore algebra, it just follows from this right here. But then in the dimer algebra, yeah, it's not hard to see that the 2 unit cycles at any vertex will be equal. The center of the dimer algebra A on sigma with n at least 3 now, so n being it's a 2n-gon, so we have at least a 6-gon, is just a polynomial ring in one variable. So namely, it's the K algebra generated by the product of the unit cycles, one at each vertex. And we'll see this later with the in the context of cluster algebras. And this is just, so it's just a polynomial ring in one variable. Thus, there can be no interesting interactions between the center of A and its representation theory whenever sigma is not a flat surface. So a torus, if it's not a torus or a disk or annulus, something like this, we won't have any of these interesting interactions. So this is why we want to use Gore algebras. Okay, so informally, we'll say a Gore algebra is geodesic if for each vertex I and side S of the fundamental polygon P, there is a cycle at I that is geodesic-like and passes through side S. That is, there are enough kind of straight line paths in the quiver. So I won't give the actual definition because of time, but the idea is that we have enough straight line paths kind of going in each direction at each vertex. And this is very similar to the zigzag path condition for Noetherian Gore algebras on a torus, which are the cancelled-to dimer algebras on a torus. And so a geodesic Gore algebra on a torus is a cancelled-to dimer algebra. So these geodesic Gore algebras are directly generalizing cancelled-to dimer algebras on a torus. Okay, so recall that sigma was our product of all the variables. And suppose that lambda, and this is joint work with Karen. Suppose that lambda is a geodesic Gore algebra. Let P and Q be cycles in Q. Then the homology class of P equals a homology class of Q if and only if the monomial of P equals a monomial for Q times some power of sigma. So in particular, if sigma is smooth, then P and Q are homologous if and only if eta bar of P equals eta bar of Q times some power of sigma. Consequently, a geodesic Gore algebra reflects the topology of the surface in which it is embedded. So this is saying the Gore algebra really sees the topology of the surface. And we'll see how this works in just a minute. Okay, the next result is that suppose lambda is the geodesic Gore algebra, then the center R of lambda is given by the K algebra generated by the intersection of the vertices of the tau bar images of the vertex corner rings EI lambda EI. And remember, tau bar is just the simple matchings, so we don't need to worry about all the perfect matchings. We only keep the simple matchings, and the tau bar is the monomial made from these simple matchings. So just like we saw on Wednesday. If R is non-Noetherian, so we'll see that this is often the case, then it is depicted by the cycle algebra. And by this we mean this K algebra generated now, instead of by the intersection, by the union over the vertices of the tau bar images of these vertex corner rings. So on a torus, transitivity implies that EI lambda EI is the same isomorphic to EJ lambda EJ for each IJ in each pair of vertices I and J. So on a torus, for a geodesic Gore algebra on a torus, R and S are equal. And so what's happening is you have this R and S are equal on a torus, but as you go to higher genus surfaces, this is really kind of due to the curvature, that the surface has non-zero curvature. The R and S kind of separate, and we'll see how they interact in just a second. Okay, so this theorem now tells us how the topology is related to of the surface is related to the algebra. So the CARW dimensions of R and S are equal, and equal to n+1, where n was half the number of sides of the polygon. In particular, if sigma is a smooth genus G surface, then the dimension of R is equal to the rank of the first homology group of sigma plus 1, which is just 2 times the genus plus 1. So we're really getting that the CARW dimension of the center is given by the genus. And so on a torus, G is equal to 1, we recover that the dimension of R is equal to 3 that we saw before, right? Because if you put a 1 in there, 2 times 1 plus 1 is 3. Okay, so recall our dimer quiver. This one is on a torus, sorry, on a genus 2 surface. And there are 12 simple matchings that we've seen these pictures before, but now we'll use them to actually look at the center of the algebra. And we can call this x1, x2, all the way to x4, y1, y2, y4, z1, z2 to z4. We have, so the polynomial ring generated by the simple matchings has these 12 variables. And consider the cycles alpha 1 through alpha 8 that run along the sides of P. So here this is alpha 1, this one is alpha 2, this is alpha 3, alpha 4, and so on. And these are cycles because you remember we identify the vertices on the corner of the polygon. So each of these with a different color is a cycle in the quiver. And these cycles have tau bar images given by these monomials. So like to find the monomial for alpha 1, you just take all the monomial for this arrow times the monomial for this arrow times the monomial for that arrow, and then that gives you the monomial for alpha 1. Okay, lambda has cycle algebra given by this right here. So it's generated by sigma, and the tau bar images of these cycles around the edges of the polygon, and center, which looks like this. So again, this is K adjoined sigma plus some ideal in S. So it looks like the rings we considered when we talked about the non-Noetherian geometry. The center R is non-Noetherian since it contains the infinite ascending chain of ideals shown here. So the big difference from the torus case and the higher genus case is that now the center need not be Noetherian, even though it's directly generalizing Noetherian dimer algebras on a torus. For higher genus surfaces, and this is really kind of a result of the curvature, that we have non-zero curvature. Okay, and the last thing before we go on to cluster algebras is just to ask the question, is the Noetherian locus U, which was the points in the cycle algebra, the variety for the cycle algebra, are these points where R localized at n intersect R, which is equal to Sn. So these are the points where R localized at that point is Noetherian. Is this locus, this Noetherian locus, useful in understanding dimer or Gore algebras? And so I just wanted to quickly state a result to show that yes, it is useful. So this theorem is with the endomorphism ring structure of the Gore algebras. And so suppose lambda is a geodesic Gore algebra. Let n be a point or maximal ideal in U, and set M to be n intersect R, which is a maximal ideal of R. Then the localization of the Gore algebra lambda at M is an endomorphism ring over its center. So for each vertex I, it's of the form, it's an endomorphism ring over R sub M of lambda sub M times EI. And again, this goes right back to the torus, and this is exactly what happens for cancellative dimer algebras on a torus. But there, the Noetherian locus is the whole center. Okay, so the second result to state, just to show how the Noetherian locus is used, is let psi be a cyclic contraction of Gore or dimer algebras on a torus, let Q be a prime ideal of S, and set P to be Q intersect R, so it's a prime ideal of R. Then the subvariety defined by Q, or the zero locus of Q, intersect with the Noetherian locus, or intersects the Noetherian locus, if and only if the localizations of lambda at P and lambda prime at Q are Morita equivalent. So this locus U is, this Noetherian locus is very important in looking at the representation theory of these algebras and saying what happens. So there's other similar results in this direction. Okay, now what is the dimer or Gore algebra on a surface with boundary? And we will restrict our attention to the case where sigma is a disk. And this part is following or sorry, this part is based on Karen's lecture notes, Grassmannians and cluster structures. And for somebody learning about this area, these are great notes to use. I also, in this part of the talk, there was a technical problem with the pictures. So the slides that will be uploaded later will include the pictures, but here we'll need to use our imagination a little bit because the pictures, yeah, there was a technical problem with the pictures. Okay. Okay, so we can associate a quiver Q sub t to a triangulation of a regular n-gon P. So we need to use our imagination, but hopefully, well, I think many people have seen this before. And in Lauren Williams' talk, I believe on, maybe Tuesday, there were pictures of this, so there'll be a picture later. So, so how this works is you place a vertex I on each edge of T, so of our triangulation, and you draw an arrow from I to J if I and J belong to edges on a common triangle of T, with J clockwise from I, such that I and J do not both belong to boundary edges. Okay, so now label the vertices 1, 2 through n clockwise around P. So we have this polygon, so we need to use our imagination here. We label the vertices 1 through n clockwise around our polygon. And then we associate a Pluker coordinate P sub AB, where A is less than B, with an edge connecting A and B. So there's another picture here. But so on each of the edges, if you have this triangulation of your polygon, you put a P sub AB, where A and B are saying from what vertex to what vertex this edge is going. So, yeah, so for any diagonal in this polygon, you can have a PAB saying, okay, it goes from, say, vertex 2 to vertex 5. You draw this diagonal, then we would put this PAB sitting on that diagonal edge. And then the Ptolemy relations can then be obtained from P, as for example, so this one, I guess we really need the picture, but we have our, you take yeah, like you take this rectangular region in the triangulation, and whenever you have these two diagonal edges, you get this relation that looks like this. Yeah, so this really needs a picture to make this clear, but it will come with the slides. Okay, so the main kind of theorem with these was in 2003 by Fomin and Zelevinsky. So let n be at least 5 and let P be a regular n-gon, then the homogeneous coordinate ring for the Grassmannian of 2 planes in n-dimensional space is a cluster algebra, and it's given by these P sub ABs, these Pluker coordinates, modulo these Ptolemy relations, where A and B run from 1 through n. And the cluster variables are these Pluker coordinates, and the ABs are the diagonals in our polygon P. So furthermore, the seeds are in bijection with the triangulations T of P, and the quiver of a seed is given by what was defined on a previous slide. And cluster mutation just corresponds to, in a quadrilateral, you flip a diagonal, and what that will do in the quiver is it will correspond to a quiver mutation in quiver, QT. which is completely amazing how that works. So again, yeah, flips of the diagonal edges in a quadrilateral if you have your triangulation, flipping from, say, one diagonal to the other one, what that does to the quiver is the same as a quiver mutation. Okay, now we can turn the quiver Q sub T of a triangulation into a dimer quiver Q by adding arrows along the boundary called boundary arrows. So now our quiver we had before, one of the conditions was that if two vertices are on sides of the polygon on these boundary edges, and you have this, you don't connect the vertices if in a triangle if they are both boundary edges, on boundary edges. So now you do include these boundary arrows, and for dimer algebras A in this setting, you do not take the cyclic derivative of the dimer potential with respect to the boundary arrows. So I should just say, yeah, people have studied it both ways. If you do take the derivative, the cyclic derivatives with respect to the boundary arrows, you get a finite dimensional algebra. If you don't, then you get an infinite dimensional algebra. And in this context with the setting of cluster algebras, the right thing to do seems to be you don't take the derivative with respect to these boundary arrows. There's another picture missing here too. Okay, so now let E1 through En be the vertices along the boundary of Q, and set E to be the sum of these vertex idempotents along the boundary. Then the boundary algebra of Q, so this was introduced by Karen, Alistair King, and Bethany Marsh, is the subalgebra, which is B is E times A times E. So it's just, yeah, it has a vector space. It has a basis consisting of paths from one boundary vertex to some other boundary vertex. And the boundary algebra B of the example that wasn't shown on the slide is given by this quotient here. Okay, so this is for a particular example that's missing from the picture, so use your imagination. And here the X, well, okay, I should say, so this gamma here, this quiver is just a cycle quiver where we have n vertices going in, so we have this going in this circle, and there's an X arrow, say, going clockwise from I to I plus 1 around our quiver, and a Y arrow going counterclockwise. So we have X arrows going one way, Y arrows going the other way, and it just makes it's like the pre-projective quiver for an extended AN quiver, where it forms a cycle. Okay, so that's this gamma here, and the X, you just have to, you say X is the sum of all these Xi arrows, and Y to be the sum of all these Yi arrows, and then we just have these relations here. So this is actually many relations, but it's just a compact way of writing it. So you just to get the individual relations, you just multiply these by the vertex idempotence along the boundary. Okay, and just as the higher genus case, the center of B, the boundary algebra, is generated by the sum of the unit cycles around the boundary, and thus is the polynomial ring in one variable. So this is just like we had in the higher genus case. But now this is what we want because it's a flat surface and it's a, you can think, I mean, the disk is the same as a sphere with a hole in it. So it should be one-dimensional. In higher genus cases, what you want shouldn't be one-dimensional because it has a higher genus. But in this case, this is the right thing that it should be. It corresponds to the topology of the disk. Okay.
Charlie, you don't have a lot of time left.
Oh, okay, okay. So how can we generalize this cluster structure from the Grassmannian to N to, we change that 2 to any K. And it suffices to take K to be less than or equal to N over 2. Remember, N here in this setting is the number of vertices around the what we had as a polygon. Was it n-gon? Okay, so recall quickly from Monday what zigzag paths were. So a path A1, A2 through AN in a dimer quiver Q with each AI an arrow is a zigzag path if AI plus 1 is a subpath of a clockwise, respectively counterclockwise unit cycle whenever I is even, respectively odd. And equivalently, you can state this in terms of the dual bipartite graph that Lauren Williams showed. And it's a zigzag path if it turns maximally left at a vertex, then maximally right at the next vertex, then maximally left, and so on. And we saw that these zigzag paths were very important because dimer or Gore algebra on the torus was Noetherian if and only if the following holds. Each zigzag path is a simple closed curve, and the lifts of 2 zigzag paths to the universal cover intersect in at most 1 arrow. Okay, so then I'll just kind of give an informal definition here for time, but so this is due to Bauer, King, and Marsh. A Kn dimer quiver is a dimer quiver on a disk with a set of zigzag paths, pi, 1 for each vertex around the boundary, from vertex I to I plus k on the boundary, such that each path does not self-intersect and which satisfy what are Pozniakov's rules for alternating strand diagrams. So the same zigzag paths are very useful here too. And this is saying loosely that there is in this sense, kind of a set of straight line paths from vertex I to I plus k along the boundary. And a theorem due to Scott is that Kn dimer quivers exist for each k in N. Okay, and so the second to the last theorem to state is just the boundary algebra of 2 Kn dimer quivers, Q and Q prime, are isomorphic. So you can take any 2 boundary algebras of 2 Kn dimer quivers, and they'll be isomorphic, and they're isomorphic to this, where again, this gamma n has this cycle quiver with x's going in one direction and y arrows going in the other direction. And so we have this isomorphism here, generalizing what was before. There'll be a picture showing this too. And finally, by abusive notation, By abusive notation, by A and B, we now mean their completions with respect to the central element of sigma and this sum of the xi, yi's, respectively. And now Jensen, King, and Su introduced this category of Cohen-Macaulay modules. So these are B modules that are free over their center. And Jensen, King, and Su showed that this category, which is they call FKN, is an additive categorification of Scott's cluster algebra structure on the coordinate ring for the Grassmannian Kn of K-planes in n-dimensional space. And just the last theorem to state then is that a theorem due to Bauer, King, and Marsh is that there is a maximal rigid object T, which is a sum of these modules that go around the boundary of your disk. There's this maximal rigid object in our category here, such that the dimer algebra is actually this endomorphism ring over the boundary algebra of this maximal rigid object. Okay, thank you.
Thank you very much for your series of lectures. Are there any questions? Doesn't seem to be the case. You can always ask more questions in the chat and I would pass them on. And you should look at the pictures later. Now let's thank Charlie again. We resume in 10 minutes. Yeah, at the full hour.
Do you want me to?
Yeah, you can do that.
Okay. Should I do it at the beginning?
Yeah, I was going to do that, but you can.
Oh, okay.
I'm happy if you do it.
I thought we were going to do it at the first. No, that's
I was running late and Charlie was running late. So.
I probably makes sense because you're chairing. So.
Okay. No, it's sorry, I couldn't find the name.
No, that's
Demasiado.